So let's look at example 6.2. In a Little League baseball game, the 145-gram baseball enters the strike zone with the speed of 15 meters per second. The batter hits the ball and it leaves his bat with the speed of 20 meters per second in exactly the opposite direction. So what do I want you to do? I want you to do the very first thing that we talked about. Draw me a sketch of the situation. Draw me a momentum, an impulse momentum bar diagram. Okay. So what I'm asking you to do here is draw a sketch of the situation along with its bar diagram. And the reason why we want to do this here is because it will give you an overall view of this thing. Because if you don't see the picture, you have zero chance of actually solving this problem. Okay, let me give you about 30 seconds to a minute, and then I'll get started on this. Okay, this is example 6.2.
Could you scroll up just a bit so we can see the whole problem?
Sorry about that.
Thank you.
So I just saw the question that was asked that there's different types of impulses. I'm going to disagree with that. An impulse is effectively how long a force interacts with an object. People can use it differently, but the wording is exactly, it means exactly like that. So remember, these examples are on the Canvas webpage. Okay, let's start looking at this thing. So when I look at this thing, what is the focus of the question? Note, we're talking about delivered by the bat to the ball. Our focus is the ball. So note that in this situation, we only care about the ball, not the bat. But the bat is part of the question. So if you're looking at this in the language of momentum, what we see here is that we get something like this. I have a baseball. Okay, here's my baseball. So my baseball is coming in, and it's coming in with some speed, which we'll call V1, or else maybe I should start color coding these right away. Let's say that it comes in with some initial momentum P1. I agree that there's a bat, but the whole world that we care about is just contained within the baseball. That's it. And what happens afterwards? So this is, now let me move this down just a little bit. So this is what happens before. So then afterwards, what actually happens to the ball? Well, the ball leaves. We know that the bat has hit the ball, and the ball now is moving faster, or it has a higher momentum going to the right. And of course, this is what happens afterwards. That's all that matters. Our whole world is this baseball. So what we're going to do here is that we're going to apply the impulse momentum theorem on the ball to get information about the bat. By the way, I could have said the same thing with the wall. I could have said the same thing with the car. I could have said anything about that. But that's really the picture. But now if I want to sketch the situation here, what I do know is that in this picture, which is outside of our system, I have a bat. And what is the bat doing? The bat, we then say here, is that it's the bat that causes the change in momentum. We know that. And as a consequence, what this tells us here is that there's going to be an impulse. So there's going to be an impulse in the baseball due to the bat. Now note, all of these are vector quantities. So the first thing we got to do here is that we have to assign a direction. So what direction am I going to assign? My personal favorite is that if I have a situation like this where there's a change in direction, the incoming direction I choose as negative, the outgoing direction going to the right is positive. So you gotta choose a sign. So now we've seen this before. So now let's go draw our momentum bar diagram. So what do we know here? Here's our situation. So what do I see here? I see that the ball is doing what? It comes in at some high speed. And this is right before the collision. It has some momentum or speed going to the left. And then what happens here is that the speed of the ball starts to slow down until it reaches 0. Okay. Why is it doing that? Because I have the impulse of the bat acting throughout this whole situation. So now let's go look at this picture here. So if I look at my bar diagram, I'm then going to say what? Right here is where the ball momentarily stops. Okay, it stops. So what you're seeing here is that I have, now remember my direction, I called that negative. Everything going to the right, I call that positive. So everything going to the left is negative. So when I look at my bar diagram, I have to do this. And you know what? It's not low enough. I'll raise this if it's too far down. Okay, so here I go. So there's my line. And what I'm going to do here is that I'm going to say, so what is happening? The momentum of the ball is negative. So that means here you're seeing that below the line is negative, above the line is positive. So this is the momentum of the ball coming in. Now look at the frames. Look at frame 1, 2, 3. What's the first thing that the bat has to do? It has to bring the baseball to rest. So when I go in and I start drawing my impulse, look what I'm doing here. The first thing I got to draw here is that I got to draw 2 squares. Why do I got to draw 2 squares? Because you have to stop the ball. So this is frames 1 to 3. So when you're seeing this, I'm going to draw this, but it's really all the same curve here. So part of that is part of the impulse is to stop the ball, frames 1 to 3. So now what happens next? I know that the momentum of the ball, of the baseball, is then going to increase. So let's say that the ball speeds up by a value of going from 2 squares to 3 squares. So this is the momentum 2, and you could see that the momentum 2, as I've shown up here, it's in the positive direction. So you could see I've drawn this thing here. Now look what the impulse has done now. The impulse went from frames 1 to 3. So the first thing it has to do is it has to stop the ball. So now what does it has to do next? Look at the right side. The right side tells me I now have to speed up the ball from rest. In other words, I got to go from frame 3 to 4 to 5. So how much? So the impulse not only has to stop the ball, but it has to speed it up now. And so what you're seeing here is that if this P2 is 3 squares, I then have to go all the way up 3 more squares. And so when I look at this thing, this right here, this is from frame 3 to frame 5, where now we speed up the ball. So there's 2 pieces to this impulse curve, right? There's 2 pieces. So now this is the impulse of the bat. So this is our mathematical equation, right? So what you're seeing here is that you can see here is that the momentum starts negative, and then the momentum ends positively. So if I now start to look at this thing, now I could, if I want to calculate the impulse of the ball, I then go by the impulse momentum theorem. So the impulse of not the ball, but the bat is then given by our diagram. Look at P1. P1 is negative. So that means here I have to come in by hand and say this here is negative P1. So when I look at the impulse of the bat, you could see that the impulse of the bat, well, that's positive. And if I look at P2, that tells me that P2 is also positive. So this becomes a really important thing here because look at the signs of the momentum. They are opposite on each side here. So now, if I now solve for J of the bat, then I'm going to see here is that J of the bat is then going to be P1 plus P2. Look at the signs. Those signs are really important. But this is also equal to MV1 plus MV2. So note that I am adding them, not subtracting them. So then if I isolate the mass, then I'm going to get V1 plus V2, and that's a positive quantity. So then what do I know? I know the mass of the ball. The mass of the ball is 0.145 kilograms. Make sure you get that into kilograms. We know that the speed is 15 meters per second, and then the final speed is 20 meters per second. So I got to plug in those values. If I plug in these values, I'm then going to get 0.145 kilograms times the quantity 20 plus 15 meters per second, and therefore I get 5, I'm going to move it down. I'm going to get 5.08 Newton seconds for J of the bat. So I now know the impulse created by the bat. Did I ever look at the bat? No, I never looked at the bat. What did I look at? I only looked at the momentum of the baseball because something had to change it. So now if I go look at the second question on this guy here, let me go grab this. It says what? Let me copy this. So now part B reads like this. If the bat is in contact with the ball for 1.5 milliseconds, what is the magnitude of the average force exerted by the bat on the ball? Now, that's important here because we're talking about average here. So then when I look at this thing, so we're seeing here is that by definition, let me do this. I'm not gonna, by definition, we said here is that the impulse of the bat is either the area, but the way we calculate it was the change in the momentum. But this area is also, by the mean value theorem, is that time average value of the force times the time. So now I can go solve for the average force. So then solving.
Is that J ball or J bat?
J bat, thank you. So solving for J bat, then I could write then that J bat is then going to be this average force times my contact time, which then says, oh, I said J bat. I should have said the average force of the bat. So how about if I go back and rechange that, the average, then it says that the average force is then the J bat divided by delta time. So then if I plug in my values, I'm going to get 5.08 Newton second divided by 1.5 times 10 to the minus 3 seconds. And the numerical value that I get here is then 3,400 newtons for the average force. And it turns out that that's a huge value, right? Man, that's a huge force. That's a huge, huge force. So if you look at me, I'm about 225. That's like 3.5 times my weight and force. So that means that the baseball bat, the bat, hits the ball with a force of, I'm going to say about 3,500 newtons, which will then be, that's going to be what, 675, maybe around 800 pounds. It's going to be less than 800 pounds, but it's a little less than 800 pounds of force. That is a lot of force. It's amazing that bats can actually provide that type of force there.